Good morning and welcome to Making Boards Fly with AI, the next installment in the webinar series, OCTAVE Insight, Hear, Learn and Interact with Advanced Analytics Experts, organized by OCTAVE, the John Keells Group Data and Advanced Analytics Center of Excellence. So this webinar series has been curated with the intention of providing a platform for advanced analytics experts, professionals to interact with the industrial experts from the globally renowned advanced analytics consultations. So my name is Rajitha Navaratna, so I'll be the host for the day for this particular webinar. Okay, so we hope this will be an interactive session, and so please feel free to share your comments, questions, and experience in the following chat box, and we will make sure that we'll have a Q&A session at the end. We'll try to make it as much of the questions as much as we can at the end of this webinar. So feel free to ask any questions in the chat. And so let me introduce the speaker for today. Today's topic is making boards fly with artificial intelligence. So today's speaker, Nicolas Hohn. So he's a data science senior expert at the Melbourne office of McKinsey Company and the chief data scientist for QuantumBlack in Australia, the advanced analytics arm of McKinsey, and leads the analytics team. So he brings more than 15 years of experience, post with a PhD experience in research and development and commercialization of product innovation in big data analytics and predictive modeling. So he had led analytics teams to extract actionable insights from data in a range of fields, including financial services, telecommunication, retail, mining, manufacturing, and IoT, and many more. So he has experience in building end-to-end data analytics solutions using stream architecture and distributed machine learning. So it's warmly welcome, sir, to be here, and it's very exciting to have you, sir. And then I'll let you to take the rest of your the webinar from here on. Over to you, Nicolas.
Thank you, Rajitha. Thank you, everyone, for having me. It's a real pleasure to be talking to you today. Today, I want to take you on a bit of a journey, mixing artificial intelligence and sailing, which is not usually the type of journey that you think of, and not the type of application where you would think that artificial intelligence has a lot to do. Let me first play a short video to describe a little bit what we did, and then I'll go into the details of how we did it. In a nutshell, we helped Team New Zealand, which is one of the best-selling teams in the world, retain the America's Cup. The America's Cup is the oldest and most prestigious sailing trophy in the world. It's an event that happens about every 4 years, and for every cup, the teams have to build new boats according to certain rules. And we helped the team in New Zealand arguably build the fastest boat for the race, which they ended up winning. So let me take you on this journey, but first I'll share a video.
The America's Cup Match 2021. This is an epic race. Magnificent flying machine. Here we go. Here comes the push.
It's the fastest boat wins the America's Cup, and we're seeing that right now.
Emirates Team New Zealand do it again in a new class of boat that proves Kiwis can fly. Sailing's most treasured prize. The America's Cup stays in New Zealand.
The America's Cup is the oldest sports trophy ever.
Got a lot of history there, and at the same time you're blending all that history with just cutting edge technology.
Most people think of what we do as we go sailing. Well, we do, but it's not sailing. We go low flying aircraft sort of on the water with great hydrodynamic and aerodynamic qualities.
The technology and the design can really make the difference between winning and losing.
You have a simulator that's completely repeatable. You can model the same weather conditions, the boat going through the same waves. However, to to drive the simulator, you've got to have sailors involved in that when they're out on the water. And so to actually get the right people together is a real challenge. And the sailors are not completely consistent.
You know, it's something that was, you know, really cool when McKinsey came in, is that, you know, really challenged us and gave us a lot of new ideas and, you know, ways of solving solutions that we probably perhaps hadn't thought about before.
What we were trying to achieve was incredibly difficult, and I was quite sceptical. We started off by getting the agent to learn how to sail in a straight line, upwind and downwind. The crucial moment was when it all of a sudden started doing upwind times and tacks and jibes that were better than the sailors were doing in the simulator.
That was a good moment. That was the point where I was like, yeah, we've got something here that is going to be useful.
I don't think we're the first team that's thought about AI. Difference simply is that with working with McKinsey, what we now have, which is pretty unique and pretty advanced, probably doesn't exist in these other organisations.
Designers can iterate through foils in a much quicker way. What typically would take a day or several days, they can run through in a matter of hours.
Sailors, as athletes and as competitive people, wanted to ensure that, you know, there was nothing to learn from the bots, and they don't want to be beaten by a computer.
The bot does so many runs, and to be able to go down there and, you know, compare what you were doing with the bot is, you know, where we see the performance gains.
AI in this case, I mean, that's the future. I mean, if you haven't got good AI within a few years, you're not going to be on the page.
All right. So this hopefully gives you a high-level view of what we did. And now I really want to go deep in the details of what this actually means in practice for people like you and I actually delivering this type of work. So one thing to understand, first of all, is the business reasons behind what we're doing here. I'll spend a bit of time on that, and then I'll go into the technical part. But it's important to understand the value that you're trying to create here. So as mentioned in the video, those boats are doing 50 knots, which is almost 100 kilometers an hour on the water. So that's why all the sailors on the boat are wearing helmets and goggles, because it's insanely fast. And those boats go really fast because they're actually barely touching the water. You saw in the video, they're actually flying just above the water through what's called a foil. So the foils, you can see one here on the black boat on the screen, which is the Italian boat. It's those wings that they have on each side. And when the wing is under the water, it works very much like an airplane, and we actually lift the boat. And with less drag, the boat goes faster. And so the design of those foils is very central to the ultimate performance of the boat. And so that's why we spend some time with them, helping them design those foils. And the interesting point here is that all the design is done through a simulation. There is very little room to actually build physical prototypes. And that's important to understand, because that's really what drives the methodology and the way you go about building those boats. Here on this slide, I'll explain very quickly the iterative process that the team goes through when they're building those foils. You start with a foil, which is this element here on the left hand side, and the foil gets if you want, loaded into the simulator. And so the simulator has a boat with the latest design, but the simulator by itself doesn't do anything. It's a bit like, you know, a flight simulator. You have the simulator, but you still need a pilot in the simulator to actually drive the simulator. So here it's the same thing. You have sailors who spend time in the simulator to really sail the new design, the virtual design, as best as they can, and then they measure the time it takes them to do a lap, for instance, and then they can compare the performance between different designs. And because they're such good sailors, we're talking Olympic gold medalist sailors, they're sailing as well as you can. And so any difference in in performance can be attributed to the design. And that's very important for the methodology. So they do that, and then they give feedback to the designers, and then the process starts again and again. So because there's a human in the loop, obviously it's actually quite a slow process. It takes a lot of time, and it's an opportunity cost because the sailors can't be doing anything else during that time. And in addition to that, when the sailors, as it says in the video, are not fully repeatable, which means that they need to do multiple laps and average things out to really understand the performance of that design. So that's what takes a lot of time. And they do that over 3 years, but over those 3 years, they can really only design 3 pairs of actual physical foils, including the ones they use for racing. So think of it as you get 2 tests and one is the one you use for racing. So other 3 years, that's very, very little physical prototyping. And so that's why it's really important to get the most out of the simulation. And so we set out to actually building an AI system that could automatically sail the boat to replace the humans, with the aim of obviously increasing the rate at which they could do those iterations. So you might think, okay, what's so special about building an autopilot for a boat? Like, we pretty much have self-driving cars, so how much harder can it be? Well, it turns out that it's actually much harder than building a self-driving car. And that's because you have a lot more degrees of freedom. You know, where one human can drive a car, you need a team of at least 5 humans to optimally sail the boat. That's because there are a lot more controls and things to do on the boat. And so if you're thinking about how to characterize the complexity of the task, it's much, much harder than driving a car because there's just more degrees of freedom. And that's really what makes it a really interesting problem from an AI perspective. In addition to the large number of degrees of freedom, you also have a huge difference, which is that your engine, which is in this case is the wind, is obviously varying over time. So you never have a clear picture of how much power you have available, which again is very different from a car where you have a very clear mapping of the performance of your engine. And so all these things put together, if you also add the fact that you have variable wind and variable currents and waves, mean that it's actually an immensely complicated task to do. And that's why in the video you heard Dan, the head designer, saying, I was very skeptical that this could be done. So it's an interesting point because while they were always convinced that it would have a lot of value, they just weren't sure that it was feasible. And so we helped them make this feasible. And we did this through a technique called reinforcement learning. Reinforcement learning is something that some of you might be familiar with and some of you might not. So let me take you through very quickly what this actually is. If you think about AI and advanced analytics in general, and you have what's called unsupervised learning, you'll have supervised learning, you might have certain tasks that are solved with optimization in a very prescriptive way. And reinforcement learning is very much part of that optimization bucket. It's something that has been postulated for a long time, but could not be proven to actually work in practice because computers were just not powerful enough for many, many years. And I would say maybe in the last 5 or 10 years, it had experienced a bit of a new beginning with the likes of DeepMind or other industrial labs, which have proved how you can use reinforcement learning initially to play video games, like simple Atari games, for instance. The AI agent built from reinforcement learning quickly became very, very good at that. And nowadays also defeating teams of professional human players at games like Dota 2, for instance. And a few years back, I think it was 2016 or 17, DeepMind also defeated the best Go player in the world using an AI system built mostly around reinforcement learning. So in those two situations, while the task is difficult, it's actually very well defined. You have the rules of the game and you know what playing well means. Applying that to an industrial setting where you actually have more complex dynamics, where you don't have actual rules of the game, you have to kind of figure out what sailing optimally means, shows that, it just wasn't obvious that it was even doable because of all those constraints. So we went on this journey to try and figure out whether this could be done. We had a good intuition that we should be able to do it, but it wasn't quite clear how hard it would really be. And it proved actually really complex. Complex because it's an optimization problem, but you have very loosely defined goals. You have to kind of define yourself what sailing optimally means. And you also have a very imperfect knowledge of your environment. In the game, you pretty much know, you can quantify everything that's happening on the screen. In our case, all we could see was what was actually happening on the boat, but it was very dynamic in nature and very hard to characterize. So we used this reinforcement learning technique, and here's what it looks like on an actual for a simulator. So think of this little robot up here as the AI agent. So that's the virtual sailor that is learning how to sail through reinforcement learning. And the iMac at the bottom here is just a representation of the actual simulator. So the agent will send actions to the simulator. The actions are the 14 controls that we have on the boat. It could be steering the wheel, trimming the sail, moving the foils, and a range of things like that. And as is typical in reinforcement learning, you get two types of information out of your environment. One is the state. So this is just a characterization of the present state of the system as a consequence of the actions that you send to the system. And you get a reward, which is a function that quantifies how well or how poorly you're doing. So just to put this in perspective, it's a bit like, as a toddler, you learn how to run. First thing you do, you stand up, and then gravity usually pulls you back down very quickly. So you learn how to stand and be kind of stable despite gravity, and then you start walking, and then you start running. So it's very much the same principles that we applied here for the agent to learn to sail. Sailing is a very complex task, so you want to, if you want, cut it down in smaller tasks and incrementally become better at them. So we started sailing in a straight line, which is a lot easier to do, which admittedly you can do with more standard optimization techniques. And after that, the agent learned to do the maneuvers. So these are the turns. It's called a tack if it's upwind, and it's called a jibe if it's downwind. So that's fundamentally what the system learned. Up to this point, I guess I've just showed you what we did at a high level, and now I really want to go down to the meat of the problem and dive a lot deeper into how we actually did it. So because reinforcement learning is very sample inefficient, by that I mean it takes a long time to learn anything. It's a very generic and very powerful technique, but also very sample inefficient. And so the way you make it work is by having a really solid infrastructure, most likely in the cloud, so that you can really distribute the compute over a large number of nodes. And so what happens is that the agent is learning in parallel from multiple simulations. So it's not just doing one simulation at a time, it's actually learning from multiple actions across multiple simulations. And so to do that, we used an open source cluster management called Ray, Apache Ray. You can Google it and find out a little bit more about what it does. It's fundamentally a stack that enables you to do distributed in our case, distributed reinforcement learning quite in the most efficient way. And so we started by building an actual building the simulation engine. So the client already had the simulation engine, but it was only running on-prem. So the first stage was really the engineering to package that simulator inside a Docker container that you could then scale in the cloud through an API that's called a GIM environment, which is a standard way to package most reinforcement learning environments. So once you have a simulation, then you bring in the right reinforcement learning algorithm. And I'll spend a bit more time on that later, but we used a custom implementation of an algorithm called SAC, stands for Soft Actor Critic, which proved to be the most efficient learning algorithm for the type of problem we had. And as I mentioned, once you have the simulation and the learning algorithm, then you need to scale all this, because there's no way this is running on your laptop. It just doesn't have enough compute power. So we scaled it on, we ran everything on AWS. You could do the same thing on other cloud providers, using Ray, as I mentioned, and using spot instances. Spot instances, it's important to understand, obviously they're a lot cheaper, but they can disappear at a moment's notice. And so you need to build your cluster in such a way that it's resilient to having nodes coming up and down in your in the environment. Once you have built this learning environment, then you tune it so you have certain parameters. For the ones familiar with reinforcement learning, there's a scan factor called gamma, for instance, which measures how far the time horizon over which you're really managing your reward function. So there's a lot of hyperparameter tuning, which takes time. And then you're actually running a whole range of experiments. If you think of the multiple months that it took us to do this, we would have been running hundreds and hundreds of experiments. So it's very important to have a way of managing all those experiments. I don't know, if for instance you're building, I don't know, a random forest model, you try one, then you do another one, then you do another one, but you get feedback very quickly, so you can very quickly iterate and find the best model, maybe in a week, maybe less, or maybe 2 weeks. Here, we're looking at experiments that take a lot longer to run. At first, each experiment was taking 48 hours to run. So you're in the process where you're trying multiple things in parallel, and you need to be able to really keep track of everything that's happening. And so that's why you really want to manage your configurations really well. And we use the tool called MLflow to manage all the metadata around the experiments. And so all the inputs, all the outputs, which is what then enables reproducibility to go back when something goes wrong. And let me tell you, a lot of things go wrong when you're doing this over a long period of time. And once you've done your experiments, then you validate them in terms of performance, in terms of variability, and try to understand how generalizable the solution is. And we'll come back to that in a second, because that's probably the most important thing when you do reinforcement learning. And then once you've done all that, then you can actually use the tool for its intended purpose. So you put it in the hands of the designers, and they use the tool to automatically quantify the performance of their full design. So just here for a second, that's everything that needs to happen before you can actually use the tool. And then assuming you use the tool well, then you design the best possible boat, and if all goes well again, you race, and if you design the right boat and if you're a bit lucky, then you win. That's fundamentally the story. So let's go now a little bit deeper on the reinforcement learning, just to give you a sense of what we did. We tested a range of algorithms. Think of reinforcement learning and not just one technique, but there's a whole range of different methodologies that all fall under the umbrella of reinforcement learning. The biggest separation, one way to think about it, is to separate model-based reinforcement learning, where the agent has access to the details of the actual model in the environment, and model-free reinforcement learning, where the agent really treats the environment as a black box. So if I go back to this slide for a second, what this means is that this simulator is a very complex physics engine, fundamentally solving partial differential equations in real time, describing the interactions between the boat, that's the solid, and the air and the water. And all those forces combined, that's what makes the boat actually move forward. So the simulator solves for that. So it's an extremely complex model. For the purpose of what we're doing, the agent actually doesn't need to know all those details. It doesn't need to understand how to solve partial differential equations. All it needs to know is be able to map the inputs to the outputs given its current state. So that's fundamentally all it needs to know. So it does that through trial and error, but while this might seem inefficient, it turns out that it's extremely powerful. So the agent then only learns what it needs to maximize its reward. So that's really important when you're looking at building this type of system, both from a simulation and then from an agent perspective, to only really consider what you need to solve the problem you want to solve, because otherwise there's no end to how much depth you can get yourself into and how much complexity or extra complexity you can bring to the solution. So for now, look, we've got this model-free approach, which, as I said, is simple and efficient, very generic, but because it's an approximation of the actual underlying dynamics, there's a risk that if the simulation is not perfect, the agent will try to exploit any problem. And sure enough, that's what happened. I'm taking you on a bit of a journey here. I don't want to just show you the final results. I want to show you also, to be very candid, and show you some of the struggles along the way. So struggle number one, you can see the boat here that's kind of leaning on its side, and the agent is still trying to sail the boat. It just hasn't understood that this is not the right regime and that this is just not the way to solve the boat. So this illustrates a range of things. It actually illustrates an edge case in the simulator that the designers of the simulator hadn't thought of, because if a human was in the simulator, they would never run the simulator this way. But the agent, having absolutely no common sense and some kind of epsilon greedy exploration policy, is trying a lot of different things. And so it will always find edge cases which lead to the wrong type of reward function. And so what this shows is really that actually this is good, because it shows that the agent is really exploring the space of potential actions. And you want to make sure that that exploration is happening so that you have more chances of actually finding the best policy. And so what it means is that in practice, you really need to put the right constraints around the problem, and then make sure that the reward function that you build encapsulate all the knowledge you want the agent to learn. So the reward function is really the part of the problem where you bring all the subject matter expertise to solve the problem. The next problem we faced, and which is that some of you who've done reinforcement learning before would be quite familiar with, is the problem of robustness. If you think of reinforcement learning as a way of finding the optimal sequence of actions to maximize your reward function, there's absolutely no theoretical guarantee whatsoever that you're actually finding an optimal. You might be stuck in a local optimal, and also there's no guarantee on robustness. So what this means is that you might find something really good and then keep exploring and then go back down and then find something else or not. And also it means that if you run the simulation multiple times, you might actually end up with different results. So all those things we didn't want. So we spent a huge amount of our time controlling the robustness and the repeatability of the training process, so that if the designers were to retrain the model on the same input, they would get the same output. And it's interesting because it's not always something you think about as important, but in our scenario, that was absolutely essential. And the third type of struggle that I wanted to mention is an understanding of how generalizable this is. Again, one of the expectations when you do this type of work is that you train an agent to just do one task. And here one task is just sailing one type of boat. And then the question is, can you leverage that learning to then learn how to sell another design more quickly as opposed to starting from scratch? So understanding the generalizability and how meta learning works in this situation was also something we spent a lot of time doing. And ultimately, we actually managed to train the agent on a range of designs. And then we could say that, look, for any design that falls within the sphere that's defined by all the previous design used for training, we're pretty sure that the agent is optimal. So what this does is that it enables you to speed up the iteration process again, and also just limits the number of times you have to do the training, which saves you both time and money. So once we actually solve for all these problems, we actually got something running. And so this is a video of the agent controlling the boat in the simulator. The white arrows on the water, that's the direction of the wind. And so the boat is going in a straight line at the optimal angle compared to the wind. And here it's doing this maneuver where it's changing direction. On the video here, it looks really easy and smooth, but you have to understand that in practice, there's no way that you and I can do this. If you think of this as a video game, it's impossible for a single human to control the boat with that level of precision. It just doesn't work. And so you really need to have the team of Olympic sailors in the simulator, at least 2 or 3 people, to really control everything to make it look as smooth as it is here. And so we managed to match the performance of the sailors, which, if you remember at the beginning, was basically our condition for success. We needed to be able to match the performance of the sailors. And so that's what happened. We called it our Alphago Moment in reference to when the DeepMind algorithm actually decided on a move that humans usually would never do, but that proved ultimately very, very powerful. And so here, obviously, I had to anonymize a lot of themes for sharing, but all I'm showing here is that over a range of setting conditions, the AI is actually better than the sailors. And so what this means is that we can then use the AI for the intended purpose, which was to enable a fast ranking of different designs without human intervention. And so that's what we did. And so we completely revolutionized the way the designers are thinking about their work and how they go about now not just evaluating one design over multiple days, but evaluating dozens of designs overnight. So that change of magnitude of the number of designs they have access to and they can test is what then will increase the likelihood that they found a better design. And so here on the screen, what you see is that we had 9 designs, and they've been ranked from the best one on the left to the worst one on the right. It goes this way because the metric for ranking the designs is based on the lap time. So that's the time the boat will take with that particular design to go around the course. So the smaller the metric, the better the design. And you can see some confidence intervals on the measurements. And they're just there to show how the performance will change as a function of the external conditions. So we're doing this testing across a range of wind speeds so that you build a single design which ideally will be as close to optimal as possible across a whole range of different wind speeds. So this is fundamentally what we did. And then as a bonus, if you want, we also, through this process, enable the sailors to then see what decisions the AI agent was taking to sometimes be faster than the sailors. And as you saw in the video, the sailors don't like to lose against the bots. So they also then got inspiration from the way the agent was sailing the boat to then try new things on the water. So that's what we did. I just want to conclude with a couple of additional technical slides on some of our learnings. As I mentioned before, look, the technology behind this type of problem is absolutely central to its success. And so the learnings here are on multiple fronts. I think the first one is to make sure, like, as in any type of AI problem, you have a very clear path from development to production. So you want to know right from the beginning how you're going to deploy your solution, especially in this case, given how complex the solution is. Deployment to production is not just going to be an afterthought. You have to think about this right from the start, because a lot of the decisions you will make at the beginning will have a huge influence on how you end up deploying the system. So as I mentioned, we're on AWS. You could definitely do something similar on other cloud providers, but here it's AWS for this example. We pretty much used every service we could on the cloud provider. And the logic here is that you really want to focus your effort on the value-adding tasks that have not yet been commoditized, and therefore use as much high-level APIs and services as available, so that you're not wasting your time trying to redo something that already exists, if what exists is good enough for your purpose. So that's why we use SageMaker, ECR, and ECS as standards. And then on top of that, then there's the reinforcement learning aspect and the distributed compute, which, as I mentioned, include Ray, and we did everything in Python. We implemented SAC with PyTorch, and we use Ray and RLlib and Tune, which are part of the Ray package, to do the reinforcement learning and the hyperparameter tuning. And all this obviously runs inside Docker containers that can scale very easily to a large number of simulators. And so fundamentally, as I mentioned, I think it's very important to then solve those infrastructure problems early, so that then you have time to really work on what's really the crux of the problem, and that's the technical slides I showed you around how you manage robustness, how you ensure generalizability, how you manage the constraints around your reward function. And all this is what enabled us to ultimately succeed. If I had to do it again, I would actually change quite a few things. And so I'll go through the learnings in a second, but I think it's important for everyone here to understand that, look, no one is perfect. And as you do something, you learn a lot, so that when you do it again, hopefully you're better the second time. And so here I want to share some of what we would do differently if we had to do this again, across all the different levels of activities. Very briefly, look, in terms of, I put a lot of emphasis on tracking experiments, and it's not something that we did very well at the beginning, but it's something that became absolutely essential as the project became bigger and longer. So I would really encourage you to think up front about how you're capturing all the metadata around what you do, so that you can manage that much better, especially at scale, when you have multiple people actually trying different things at the same time. And also, it's important to have the right tools to be able to debug your system locally, because the beauty of the cloud is how quickly you can scale it. But when there's a bug inside your Docker container on a virtual machine that you don't actually have access to, it's actually very, very hard to debug. So you want a very good logging process, and then you want a very simple way of reproducing those problems locally. On the RL front, it's important to think up front about the meta learning and the type of task transfer strategies that you want to do. From a simulation perspective, I mentioned some of the bugs that we found, and so it's very important to think up front about the type of issues that you might face when you want to scale these this type of simulation. And in terms of hardware and orchestration, Initially, we started with SageMaker because they had a SageMaker RL, which was really good and very powerful. But if we were to do it again, I think we would probably try to use Ray, because Ray has come a very long way, and it enables you fundamentally to use even cheaper instances, which will make the whole compute cost go down quite significantly. And doing it in a way that still enables you to manage a very heterogeneous set of machines. That might seem like a detail, but it's very important to understand that you have certain machines that do the learning, so they train in the neural networks. Other machines are just there to run the simulator. And so you don't want all the machines to be the same. You really want to adapt the characteristics of like the GPU, the RAM, the CPUs to the task you're doing, so that you really maximize your compute power. Let me pause here. That's what I wanted to share with you today. And yeah, very happy to answer any questions you might have.
Thanks, Nick. Thanks. Thank you so much. So it's a very interesting talk. Personally, I really enjoyed the talk and listening to the story. So I can see now there are quite a bit of questions are coming through during the talk, and I mean, I think one of the questions you have already answered, especially the key learnings that you had during these use cases. So while some of these questions are flying in, I'll take a couple of questions and then maybe you can go through it. In terms of like when you're designing this AI and these data science type of projects, one of the key things that we need to think about is the end user, right? So the end user in here is that I can see is the medalist from the Olympic medalist from the New Zealand team. So just wanted to understand what type of involvement they contribute to this use case, and how was their first impression, especially like when they try to run this kind of reinforcement learning type of involvement.
That's a good question. And so I would say the involvement of the end users was huge. Right from the get-go, we had a lot of meetings with the end users, if only because, look, I can't sail, like I've never been on the boat like that. And so we did have some subject matter expertise on the team with people who were really, really good sailors, but they'd never sailed this type of boat. So the message here is to really engage with your end users as early as possible and really build a solution with them. It's only through their feedback that we manage to build the right reward function, for instance, which is absolutely essential for reinforcement learning. Or we would use a given reward function, and then they will look at how the boat was actually being sailed by the agent, and then telling us, yeah, no, look, that's not optimal. We can do better here. So then we'll go back to the drawing board and change that again. And so all this to say that, yeah, the end users are always probably your priority number one to engage with right all the way through the project.
I think you Nick pointed out one very interesting thing about these end users. See whether you can involve these end users from the beginning, especially from the beginning when you work on AI or data science or machine learning projects. Like I think it's a very good learning even for us. Like okay, make sure you involve the end customers or end users, especially in the beginning of the process, and go with them. The build the story or build the AI solutions with them. That's a very interesting point. And also I think there was a question I also had, especially how did you come up with these reward structures and also these reward functions very wisely? I think I feel one of the answer probably is based on this in customers experience and this expertise you know.
And look, it's definitely a hard thing, because you have no way of knowing how good your reward function is until you actually learn through that reward function. Yeah, so it's a very long time to get any feedback and then start again. And actually, I still have it here on the screen. I think one important point is that because the boat does many things, you actually have different reward functions that get kind of stitched together. And it's actually very hard to make sure that there's no discontinuity in that reward function when you go from one activity to another. And that's definitely something I would spend more time on if we were doing that again, because fundamentally, think of the agent as trying to evaluate the gradient of that reward function to figure out what to do next. And so if you've artificially included discontinuities in your reward function, that's where all bets are off.
Yeah, true. In mathematically, obviously, as you can see, we can come up with these functions, and when you start to put it in a practical environment. So the example that you showed us in the simulated example, like, in practical, it's very difficult for even for a human being to do it.
Yes.
This kind of experience. And so when you design these things, like how did you think about these extreme cases, and what was the thought process that you have put together to handle the worst case, right? For example, if something failed, okay, what was the thought process?
I would argue that, we're building a reinforcement learning system where the agent learns by trial and error, but we as humans are pretty much operating the same way to build that RL system. It's
Exactly.
always trial and error as well on another level, if you want. And you don't know in advance where the bugs or where the problems are in the simulator. You just have to try a few things and then realize, oh, that stopped, and then go and debug it and figure out why it stopped. The problem is that there's a lot of reasons why something doesn't work when you do RL. And so you have to try a lot of things before you realize that that's actually a problem with the simulator. Luckily, because we're very close to the client, we had very good support from the client to fix any problem in the simulator. You have to understand it's a very complex piece of C++ code, and it takes a lot of domain knowledge to actually fix any problem. But it was more of an iterative process. And look, after a while, we got to a place where we had a super stable system with no more problems from a simulation perspective. But it was interesting to see that you can use a simulator which inherently has a lot of problems, but as a human, you will never find those problems because you never use the simulator in the regime where the problems are.
Yeah, and in this reinforcement learnings, like in the environment, is a major component when you design these things. So did you also look into this some of these environments, especially including these weather factors? Like, I believe it looks like in the video that you showed me that the weather was a very clear kind of environment during the race. Like, did you also think about like what will happen if it is raining or maybe?
So external factors, the rain not so much. The main external factor is the wind.
The wind,
obviously, because the wind is what will power the boat, and the wind is also what creates the waves. So the main external factor that you consider is the wind. So the beauty of the simulator is that you simulate the wind. You can simulate the stochastic process for the wind, and where the simulator is good is that then you can actually simulate with the same seed exactly the same stochastic process for another design, so that you're really comparing the designs in exactly the same conditions. And that's the only way you can really make those design decisions about which design is better. Whereas when in the early days, when all the testing was done on the water, they had only very approximate measures of those external factors. And you have to understand that the wind is actually different on the water and the top of the mast. So it's very hard to even have a single number. And so all those things mean that in the simulator, you really control those external variables, and in a way that makes it a lot better to have a repeatable system to really compare very fairly the different designs.
Oh, okay, thanks. Just have one last question for my end. So you were talking about this, the managing the experiments, especially some of the experiments were running for like almost 2 days and using ML4. Like, what was the did you think about like how can we optimize these kind of models running in these cloud environments? And did you do any optimization to reduce this
Yes.
training for these models?
We did a huge amount of optimization, and it comes in many flavors, and I think that will answer some of the questions in the chat as well. The first one is on the choice of algorithm. Some algorithms are a lot less sample efficient than others. For the ones who know a little bit of reinforcement learning, we have an algorithm called PPO, for instance, which is really powerful, but it's just really, really slow. And so we were ready to trade off some of that to get something that would converge faster, even if it was a bit more variable. So that's where SSC came in the picture. And then from so that was the first way we reduced the overall compute time through a better algorithm. And then there's also a more efficient way of using the compute itself. So you want to be fine-tuning your instances to really match your needs. And ultimately, in the end, we could then, if at the beginning it was taking 48 hours, by the end it was only taking 10 maybe. So we managed to also reduce the overall time it took to train the system.
Okay, thanks. So given the time, I'll just go through like couple of questions that the audience has asked. Let me pick a few questions. So the first one is, just want to understand why didn't you try something simpler than reinforcement learning?
So that's a good question, and I think it's the first question you should ask yourself. Is like, I would never try reinforcement learning as the first option, given how complex it is. And so, and look, in any AI, so in any situation, if a linear regression solves your problem, you should absolutely use a linear regression. Here, it's not quite that simple. But so what happened is that when the boat is in a straight line, you can actually solve the optimization problem with much more traditional techniques. But you can't solve the dynamic nature of those maneuvers when the boat actually turns. So we needed reinforcement learning because there was nothing else that would work when during those dynamic maneuvers. And that was the only reason why we used it, because the client actually was very sophisticated. And so they already had a solution to go in a straight line. So that was really good for us because that gave us a target or a baseline to measure ourselves against. And so we could go as fast as they could in a straight line, and then we could also do the turns. But yeah, it's always pays off to explore simpler options before going for something as complex as reinforcement learning.
Exactly. I hope it answered your question. I mean, given we are start to discuss about the reinforcement learning, let's take a couple of questions regarding that. Like, so how did you choose the reinforcement algorithms at the end? You were testing these things and different. So what was the decision point?
As I mentioned in one of the previous slides, I think it was this one. We actually tried a range of things. We tried PPO, we tried DDPG, and in the end we settled on SAC because it was the one that was giving us the best trade-off, if you want, between exploration and exploitation with a minimum number of samples. And it does that by keeping what's called an experience replay buffer. So it can evaluate its performance on past information. It doesn't need to interact with the simulator every time it needs to figure out whether it's good or bad. So that fundamentally, this brings more stability and also more computational efficiency. Look, this is what we're doing at the time of the project. It could well be that next year there's a new algorithm that's even better. So I think it's always important to keep track of progress here, but for now, that's what we would have used.
Yeah, I mean, naturally, these reinforcement learning algorithms are that's a little bit of unstable algorithms. So there's a question here as well, like how did you manage to create a robust output using reinforcement learning, which actually wins the competition?
A little bit. It's probably where we have the most intellectual property, so I can't just share absolutely everything because that's where we spent the most time, to be honest, because it's definitely one of the main issues. And ultimately, we we found a way through managing the replay buffer. So that's the buffer of experiences that each learner creates, by being more clever about which of those experiences in the buffer you actually use and sampling them differently. That's what enables you to get to a better solution in our scenario. I'm not claiming that that would always be the case, but it's something that we spent a lot of time on. I think it's not hard to get something that performs really well every now and then. It's much harder to get to something that consistently performs well.
Okay. So let's go through a few more questions as well. So yeah, so while we were in the topic of the reinforcement learning, so how would you structure this optimization objective for such a multi-dimensional problem?
Yeah, so as I said, look, we actually had slightly different objective functions in the different regimes that the boat was into. Like if you go in a straight line, you're optimizing for certain things. If you're going through a turn, you're optimizing for something else. And actually what happens in practice is that you will actually decompose the turn into multiple sections again. So there's definitely a time dimension to the objective function. Ultimately, look, you're still only optimizing for one thing at one point in time. And so a lot of the challenge is how you bring together all those different constraints and cost functions into a single function. And that's where I think a lot of the complexity is, because you do that and then you forget what you've put in your cost function and the system doesn't work, and you try to debug everything else until you remember that maybe it's a problem in the cost function. So my learning here is to really find the best possible way to measure absolutely everything you do and log everything and have everything in TensorBoard nice and easily accessible, because you will spend so much time trying to figure out what's not working. Let's face it, most of the time this thing doesn't work, and you're really trying to find what will make it work. So really being able to instrument everything to provide as much visibility across all the different dimensions of your reward function is what will ultimately lead you to the best one.
Thanks. Also, people are asking just about the team structure of the use case,
Yeah,
you did mention in the beginning that you were involved in this, the Olympic gold medalists, who are the other.
So I'll talk about the people we had on the QuantumBlack side, and then I'll talk about on the client side. So on the QuantumBlack side, we had a mix of, we had 2 data scientists, we had a cloud engineer because of the heavy infrastructure element, and we had a professional Python developer. So because of the size of the code base, we felt the need to actually have not just a couple of data scientists doing the coding, but also a professional Python developer who's used to working in this type of environment, but who set things up in ways there's no way we could have done it ourselves as data scientists, which ultimately made the code base a lot more robust, a lot easier to test as well. And so on the client side, obviously we had support from the boat designers and from the sailors, and it's really through a combination of those different teams that we managed to do it. The interesting thing here is that, I don't know if you noticed, but I didn't mention any data engineer, and that's one last point I wanted to make, is that in this situation where basically all your data is synthetically generated by the simulator, there was actually no need for data engineering. All the data we needed came straight out of the simulator. So the message here is that adapt your team to your needs and don't just replicate the team you had on the previous project. Because it was new for us as well to have this type of team composition for this problem, but that's what worked ultimately.
It's very interesting, very interesting, Nick. I mean, there are a few things that you mentioned also, like about the data scientist and having a professional, a Python developer or a software engineer into the team, right? So,
you have to know your limits.
Yeah. You have to know your limits and what your role is exactly. So it's a very good point for the guys. I think we are running out of the time. Just for the curiosity, did you also like look into the competitors of this particular race? And did you also come up with some type of like a simulations how they going to play in the particular race?
So no, we were very much focused on helping them design the boat before the race. I'm sure there's plenty of things you could do to help during the race, but the rules are such that you need 11 sailors on the boat, and the rules specifically say none of those sailors can be robots, so they're all humans on the boat. So they actually limit the AI assistance that you can get during the race. There's no limit to how much AI you can use before the race to design the boat, but during the race, it's very much the humans in charge.
True. Exactly. Thanks, Nick. I think we are running out of the time, but so we'll stop here. And I mean, personally, I had a fantastic time to listening to this webinar and listening to some of these designings, and especially with the decision points that you guys are looking into. And also, one of the key interesting things is try to involve these end users from the beginning, especially involve the involvement to the solution designings. So which was good to see, and also the team structure was highlighted as well. So let me finish here. So thank you all for attending this fantastic webinar, and I hope you learned something new today. Obviously, I did, and we hope to see you again in our next OCTAVE webinar. And please follow OCTAVE on LinkedIn and get updates on future events as well. Recording of this session will be available on the OCTAVE YouTube channel probably in the end of today. And before you wind up, so there will be a feedback form and the link will be there in the chat. Please take few seconds or a minute to fill out, and then we really appreciate your comments and the feedbacks on how we can improve these type of sessions in the future and what type of topics we should look into, especially to interact with the advanced analytics, especially in Sri Lanka. And good afternoon, everyone, and stay safe. Thank you.
Thank you.
Thanks, Nick.